Hi, this is bitluni and today I will show you my new LED wall.
It's an RGBW display with nearly 2000 ping pong balls as pixels. I will show how I built it and what design considerations make this superior to my previous versions. If you are new to my channel, you should know that this is already my third version of a ping pong LED wall. My plan was to make a more professional and less labor-intensive version this time. It has a lot of improvements that are not obvious at the beginning, but I will point them out through the video. The scalability is a major point. I suffered a lot during the build of the first one and even built a hole punch tool for the second one to ease up things. But it still was quite labor intensive. This time there are no holes, no painting, and the size is only limited by the wallet. Okay, I still had to do some work to assemble it, as you will see. But it's a prototype and there are easy solutions that could allow anyone without any maker skills to build one quickly. So let me start at the beginning. In the prior versions I used these WS2811 chains and installed them manually on a metal plate. This was the step I wanted to get rid of first. This was most labor intensive and limited the whole thing to one LED type. I designed quite a few printed circuit boards during the last year, so I thought why not trying surface mounted LEDs this time. Not only there are more LED types available like this RGBW I'm using this time, but I can also order them assembled on a large panel with a pristine matte black finish directly from the factory. So I started to design a system where I can easily put together an arbitrary shaped LED wall from smaller panels. Once the design was finished, I was ready to order it. And here is where PCBWay comes into play. I was in contact with them for years already, looking for the perfect project to test their PCB assembly capabilities. And they agreed to sponsor this one. I'm very thankful since this wall required a lot of components, large PCBs and a lot of assembly. If you are a new customer, you will get a $5 coupon which you can use to order the first set of PCBs. They also offer flex PCBs which I already have here for another project. But for this one I needed their assembly service which also supports through-hole soldering. I entered the details for the different sets of boards I needed and added them to my cart. In there you will be asked for the Gerber files, the BOM file which contains the part specifications, and the Centroid file which tells the pick-and-place machine where to put the parts. After the submission the order will be reviewed and you will be notified by a service person that is assigned to your account. They will source the components you specified for you. Or you can just tell them to take any substitutes. I was really anxious to get everything right because of the size of the order, but my experience was overall very pleasant. If you are interested in their services, please use the link in the description so they can continue to support my projects. The huge order arrived 5 weeks later. And did it work? See for yourself.
Guys, it's happening.
The corner pieces where the LED panels plug in are panelized. I've designed different shapes for different corner layouts. And this here is my personal touch to trigger OCD people. They have terminals for power and dip switches that help routing signals in different directions. So the wall layout is really flexible. As you can see, this was a mixed assembly with through-hole and surface mount components.
Ta-da! This looks so good!
The LED panels are surface mount only. I left the male pinhanders out since I wasn't sure if I wouldn't use another type of connector. For these 30 prototype panels it was okay for me to solder them myself. But when these should go in series I will order them with the final connector pre-installed. Probably rather with one of these types. This is how the corner piece plugs in. There are even mounting holes for zip ties or PCB standoffs if needed. These will hide behind the ping pong balls later.
Cool.
I made a test sketch for these RGBW SK6812 LEDs to test the panels row by row for each color component.
Moment of truth. Oh wow. Yeah. It works.
To solder the pin headers, I made a jig where I can plug in the headers and solder on the panel. After soldering, I can directly test the panel. All that only needs to be done 30 times. From all the 1920 LEDs, only one was faulty, which is not bad considering how sensitive they are. The function of the LEDs wasn't tested in the factory, only the electrical continuity of the PCBs. I replaced it. Next thing I wanted to test is if the LEDs survive having ping pong balls being directly glued on top, regardless of all the warnings in the datasheets. As a placement helper, I designed a 4x4 grid and 3D printed it using YouTube Magic. The gluing might also cause some heating issues, but the huge ground planes should dissipate a lot of that. My first gluing attempts have been quite clumsy. But in the end, it worked. Before we glue all the other ping pong balls, we need to prepare the base for the panels and mount the corner pieces. I made it as cheap as it gets from OSB and basic slats. It's only for structural support and will be hidden behind the panels.
Oh wow.
Due to small variations, I installed corner piece by corner piece and left the panels on to check for squareness. This whole process can be streamlined by using a template sheet and pre-drilling the holes. I imagine that could be even done with a big CNC. The pin headers and the panels seem to be flexible enough to compensate for small imperfections.
Woohoo! Okay.
Look at this, doesn't it look awesome? In the meantime, I also thought of an alternative to all the ping pongs. How about printing whole sections? That would simplify things and get rid of the gluing process. It looks like a solution, but I would need quite a few mana potions to print it using YouTube magic. And FDM printing would take too long for my single printer in the desired quality for now. But it's definitively a solution. For this prototype I will go with the gluing of the 2000 balls to see if that causes any long-term issues. Okay, let's do the ping pongs next. This is the last one. At least I thought so.
That's it. Yeah.
We are ready for the first test on the wall. First thing would be to supply the power, and that completely without any noisy fans. I will use the configuration I have shown in my last video. But we also need to configure the corner pieces to route the signal from panel to panel. In this corner of the panel we have the input pin, and down there the output, but we have also bus lines to route the signal to adjacent corners. If we want to route the signal to the next panel in row, we simply have to switch a few dips. This will route it up using a bus on the panel, and this will route it over to the input of the next panel through this corner piece.
Okay.
And now the complete wall. Continuity seems legit. To handle the amount of data of that many pixels, I will use the ESP32 again. The ESP32 cam will be perfect, just like for the old LD wall. This time I'm using my programmer board as an interface and soldered on some connectors to the usable pins that are broken out there. Unfortunately the old code doesn't work anymore since we have an additional color component per pixel. I extended my library to also support RGBW LEDs now and uploaded a simple test pattern. To the wall! It worked like a treat. But before we can plug in all the panels, we need to distribute the power a little better. At this point the wall didn't have a proper stand yet, and you can see it leaning while I work at it. And that's where it happened. The wall tipped over and crushed the panels. It took my camera and spilled my soda pot. That was devastating. Thankfully no unfixable damage has happened, except to my soul having to do the gluing again. it's my life now. A day later, I made a stand with a counterweight and continued to spread the power lines. Before attaching anything, I tested the polarity of the corner pieces to not fry the panels. There still was one problem with the performance of the wall. The last wall achieved 30 frames per second at 1200 LEDs with 3 colors per LED. Now we have over 1900 LEDs with 4 colors each. That would result in under 20 frames per second, which would be perceived as a slideshow. This needed another solution. Instead of the I2S serial mode, I could use the parallel mode with 8 channels. However, that required a complete different implementation, which I also added to my ESP32 lib. Reconfiguring the wall to a channel per column, we can utilize 6 of the channels directly and achieve 74 frames per second. We could use even more channels by mapping subsections, but that's sufficient for now. I also needed to reconfigure the corner pieces to work column-wise now.
Yeah, okay, yes.
I crimped the wires for the power supply and the data lines and connected them to the entry points of the wall. On attaching the different columns, the signals seemed to be broken, but I was sure I could solve that later.
This is massive. Look at this.
Doesn't it look cool even without the LEDs on? Let's turn it on. The flickering is still there, and I also forgot to configure the rightmost corner pieces. That was easy to solve. The flickering, however, wasn't as straightforward. First I tried to add a distinct ground line, even though all the ground is connected through the panels, but that didn't solve it. The fact that the outer columns with the longest data lines were affected most was a hint to try shielded cables. I had a few spare ones from the build of my pick-and-place machine. That finally solved the issues, except for a slack joint in one panel. Here is where the improved repairability shows the best. In a professional setting, the broken panel can be quickly swapped. Let's turn it on. Okay, here's the actual first successful test. I had to reduce the exposure so you can get an impression of the beauty of the colors. Let's compare it to the older version. The rainbow pattern first. That the balls are more dense is obvious, but it also looks tidier. I love it. Let's test full brightness white. The true white color component adds a lot here, but it can also be used to reduce the power needs when using white instead of the mutual parts of the RGB levels. Mike Harrison mentioned this in his Hackaday SuperCon talk, so check out if you are interested to learn more tricks from a master. Speaking of power needs.
Okay, the best part.
Here is the difference in noise between the two walls.
That's what I wanted. Yeah.
Okay, that's enough.
Oh, cool.
As a nice extra, I extended the driver in my Arduino library to use the same graphics interface that I used for my VGA implementation. So we can use my old examples like this real-time ray tracer which runs at 60 frames per second here. That's really cool. And we can also use the old image converters. It's still in an alpha state, but I will update you on that. Last but not least, let's try the camera.
Wow, cool.
And this everything is running on the ESP32. I'm very happy with the current state already, and I hope you have been inspired or at least a bit entertained. I put links to all the stuff and the resources I mentioned in the description. Again, big thanks to PCBWay for sponsoring this project. If you don't want to miss updates on this or other cool projects, consider subscribing to my channel. A huge thanks to all my supporters. I hope you had fun looking behind the scenes on this project. That's all for today, and I see you next time. Bye!